What we see is three graphs, and we may only have time to talk about the two on the right today. We see three graphs. The one on the far right is what I'm going to regard as the position function. Tells where the particle is with respect to some 0 point. How far on the positive side of it is. If it's above, it's going to be how far on the positive side of 0. If it's below, it's going to be how far on the negative side of 0. So as I move the slider, basically seconds are ticking away, it starts right at the origin, right at this point. And then we're going to let 1 second go by and see where it is after 1 second. After 1 second, the particle has reached a point where it's 3 units on the positive side of the origin. So what's going to be more comfortable? If we think of the particle as moving to the right and to the left, or if we think of the particle as moving up and down? What's more natural?
Up and down.
Up and down? Well, visually on the graph it's moving up and down, so maybe that's better. So the particle starts at 0, and then 1 second goes by, and it's reached a point 3 units above that. And then another second goes by, and it's only gone up 1 more unit, so now it's at a point 4 units above the 0 point. And then the clock keeps ticking, but what's happening is the particle has basically slowed to a stop, and now it's going to come back. So it's going to go for another second, and a second later, it's back down only 3 units above the 0 point. And then we're going to just let 1 more second go by, and after 1 more second, the particle is back at 0. So that's what it does. In 1 second it goes up 3, and the next second it goes up 1, in the next second it goes down 1, and the next second it goes down 3. Now, throughout its journey, what's happening is the velocity of the particle is going from a positive 4 meters per second down to a negative 4 meters per second, because we can track the velocity by looking at the slope of the tangent line to the graph of the position function. Let's start back here. I think we can look at the tangent line. The tangent line is this broken line here, and calculate the slope just kind of by looking at it. It looks like rise over run. It goes, what, up 4 and 1 to the right. So the horizontal units are seconds, and the vertical units are meters. Some appropriate unit of distance. I'll just call them meters. So if we divide 4 meters by 1 second, that's 4 meters per second. So initially, the velocity is positive 4 meters per second. Now, velocity has direction. So positive, if the particle is moving up and down, we're going to say positive is up. So initially, it's going 4 meters per second straight up. Now, something's slowing it down. Now, this is it's only slowing down at the rate of about 2 meters per second each second. So it's not Earth's gravity. Earth's gravity is going to slow it down more than that. But something's slowing it down. Slowing it down at 2 meters per second each second. So if we let another second go by, and it's right there, what's the slope? If we're right there and we look, we go up 2 and 1 to the right. So 2 meters divided by 1 second, it's only going 2 meters per second. And then we let another second go by. Whoops. What's the slope now? 0. So at the beginning, it's going 4 meters per second, and then 2 meters per second, and then 0 meters per second. It's basically stationary at this point. And then the velocity continues to decrease because a second later, what's the slope? -2. That means it's headed down. It's headed down at the rate of 2 meters per second. If you think 2 down, 1 to the right, so it's going to be a slope of -2 meters per second. And then Another second goes by, and it's well, it's speeding up, heading back toward the initial. Like I said, it hits if there's something solid where the initial point was. It hits it at a rate of 4 meters per second. Now we can calculate the velocity at any point by examining the slope of the tangent line, or we could take the derivative. Now this parabola that you see here is, if you use t's instead of x's, it's s of t. GeoGebra doesn't like to use t's for the independent variable. But it's s of t equals negative t squared plus 4x. If we take the derivative of that using the power rules that we've used, it's going to be negative 2x plus 4, and that's the graph of this straight line right here. This is the velocity function in the middle. The velocity function starts at 4, and then it's 3, and then it's 2, and then it's 1, and then it's 0, and then it's negative 1, negative 2, negative 3, negative 4. So one way of tracking the velocity is to keep track of the slope of the tangent line. Another way of tracking the velocity is to find the derivative and just look at the velocity function right there. So this is kind of what's going on as the particle is, its velocity is decreasing by 4 meters per second each second. Let's see, I don't know that much more needs to be said, except if you want to take it one more step and you want to ask yourself, what function describes how the velocity is changing with respect to time? What function are we talking about in that case? Acceleration. See, throughout the process, the velocity is negative 2 meters per second. And so that's the slope of this curve. If you look at the slope, it's 2 down and 1 to the right. So that would be negative 2 meters per second. So that's the constant velocity. And so if you look at the acceleration, this is the acceleration function. It's a horizontal line 2 units below the x-axis. So it's a constant negative 2 meters per second. So this is kind of, we'll look at this again